When Edwin Hubble turned his telescope to the newly discovered Andromeda galaxy in the 1920s, he made a shocking discovery. The galaxy was moving away from us, and not only that, receding faster than its distance from us would suggest. What he saw was not just galaxies moving apart because of some local gravitational interaction. It was the entire universe expanding. And it's this expansion that we can observe today. As light from faraway galaxies gets stretched, their wavelengths grow, shifting them toward the red end of the spectrum. The farther away a galaxy is, the faster it appears to be receding, and that speed, Hubble found, is directly proportional to that galaxy's distance. This relationship between distance and speed is now formalized in a law of physics. Hubble's law. Galaxies are running away from each other, and the universe itself is getting bigger. Hubble's discovery led to the Big Bang theory, which holds that our universe began hot and dense, and has been expanding ever since. If all galaxies are flying apart at speeds proportional to their distances, then surely we would see equally distributed redshifts across the entire sky. In other words, the universe should be expanding in all directions equally. That's not what we see. Scientists have noticed that certain galaxy clusters, including those in the Laniakea supercluster, to which our own Milky Way belongs, appear to be drifting together toward a spot in the sky known as the Great Attractor. At first, astronomers thought these motions were mere anomalies, perhaps driven by invisible mass, dark matter, or a large but nearby galaxy not yet discovered. But as more data came in, it became clear that these were not random movements. They formed a coherent pattern that defied explanation. In 2003, a group of researchers led by astrophysicist Daniel of Harvard published a paper detailing the extent of this phenomenon. Using data from the Sloan Digital Sky Survey, which had mapped about 1/5 of the night sky, they identified 600 massive galaxy clusters. They then calculated the velocities of these clusters by measuring how fast galaxies within them were receding or approaching. When they plotted the velocities against the direction of movement, they discovered that while most of the points were jumbled, a handful of them fell along a straight line. These were not normal, peculiar velocities caused by gravitational interactions. Instead, these galaxy clusters were traveling together at extraordinarily high speeds of up to 4 million kilometers per hour toward the Great Attractor. Something was pulling them together, but what? One possibility is that these anomalous motions are an illusion, statistical fluke arising from our inability to map the universe perfectly. Perhaps the true distribution of galaxies is so complex that we are simply not seeing the full picture. However, this idea has been ruled out by later studies. A 2008 study by a team led by astrophysicist Wendy Friedman of the University of Chicago analyzed data from the 2-degree field galaxy redshift survey, which had mapped a much larger area of sky. And they, too, found evidence of streaming motions in galaxy clusters. Moreover, follow-up studies have shown that the effect holds for much smaller scales as well. Even galaxies that are not clustered together in superclusters appear to be drifting in the same direction. So what exactly are we seeing? One possibility is that the dark flow is being caused by the gravitational pull of something huge. Think of it like when you walk past someone and feel their gravitational pull. You wouldn't think you're moving toward anything in particular. Your motion is too small in comparison to the size of the planet you're on. Similarly, if you're a tiny galaxy far away from the edge of the universe, the effect of the dark flow might be unnoticeable. But if you're at the center of the universe, everything should appear to be streaming past you. In this scenario, the dark flow may not be a flow at all, but a simple response to a hidden mass outside of our observable universe. But there's a problem with this explanation. According to the best models of cosmology, there shouldn't be enough mass outside of the observable universe to account for the streaming motions. Another possibility is that the dark flow is not caused by a gravitational field, but by the movement of our universe through a medium outside of itself, like a cosmic swimming pool. Unfortunately, this idea runs into its own set of problems. Our universe is filled with radiation left over from the Big Bang, and that radiation exerts a pressure that would prevent any large-scale bulk motion. So either we are missing something in our understanding of gravity, or our universe is not as isolated as we think. So maybe it's not even a closed system. Perhaps our universe is open, with new regions of space and time continuously created outside of our observable horizon, carrying new galaxies and stars, planets and people, perhaps even other universes. If that's the case, the dark flow might be a glimpse of what lies beyond, a hint of the multiverse. Next time you look up at the stars, remember, we may be seeing not only the universe we know, but others as well. The more we learn about the dark flow, the more we may discover about the nature of reality. And if you want to learn more about reality, you should check out Brilliant.org, whose support makes this episode possible. On Brilliant, you can find courses on a large variety of topics in science, computer science, and mathematics. All of Brilliant's courses come with interactive visualizations and follow-up questions. Some even have videos for demonstration experiments or executable Python scripts. Whether you want to know more about the world around you, or you want to brush up on your math skills, Brilliant has something for you. What is the fastest thing that you've ever seen? Is it a car speeding past you on the highway, a bird taking off from a tree, or a rocket blasting off into space? Whatever it was probably nowhere near as fast as the universe itself. In fact, in this video, we're going to talk about some objects that move so quickly. They could travel from one side of our solar system to the other before you finish your cup of tea. Before we get started, be sure to stay tuned for more videos like this one. And let's take a look. Dark flow. To understand dark flow, we first need to understand how astronomers measure the motion of galaxies on the largest scales. There are two main types of motion we need to consider: cosmic expansion and peculiar velocities. Let's start with the cosmic expansion. Back in 1929, Edwin Hubble made a groundbreaking discovery that changed our understanding of the universe forever. He found that galaxies are moving away from us, and the farther away a galaxy is, the faster it seems to be receding. This observation led to the idea that space itself is expanding, carrying galaxies along with it. Every point in space moves away from every other point, and the greater the distance between them, the faster the separation. This relationship between recession velocity and distance is now known as the Hubble flow. But galaxies don't just ride passively on this expansion. They also have local motions, called peculiar velocities, caused by the gravitational attraction of nearby structures. For example, the Andromeda Galaxy is moving towards the Milky Way, not away, because of their mutual gravitational pull. Despite the overall expansion of space, these local motions are expected and well understood on small scales such as galaxies, groups, and clusters. However, on the largest cosmic scales, beyond hundreds of millions of light-years, the Hubble flow dominates. Peculiar velocities should average out, leaving a smooth expansion, or at least that's the prediction of the standard model of cosmology. The cosmic expansion. To measure motion on truly vast scales, astronomers rely on the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. Imagine you're standing by a river watching the current flow past you. You might think the water is still because you're only seeing a tiny section of it. But if you could step back and see the entire river, you would notice that the water is moving. That's kind of like what's happening with the CMB. As the universe expands, space itself stretches, and the CMB, which is like the fabric of space, gets stretched along with it. This stretching causes the wavelengths of light to get longer, shifting the light towards the red end of the spectrum. Astronomers call this redshift. By measuring the redshift of distant galaxies, they can calculate how fast those galaxies are receding from us due to the expansion of the universe. This helps us understand how the universe is expanding as a whole. Now let's talk about peculiar velocities. These are the speeds at which galaxies move through space relative to the cosmic microwave background. In other words, they re the speeds at which galaxies move relative to each other, when you take the expansion of the universe into account. For example, the Milky Way has a peculiar velocity of about 250 kilometers per second relative to the CMB. That means that as the universe expands, the Milky Way is also moving through space towards the constellation of Leo at that speed. Peculiar velocities are caused by the gravitational pull of nearby matter. For example, the Milky Way and the Andromeda Galaxy are attracted to each other, and their mutual gravitational pull affects their motions. In fact, all the galaxies in the local group, the cluster of galaxies to which the Milky Way belongs, have peculiar velocities that reflect the gravitational influence of neighboring galaxies. But what happens when we look beyond the local group to much larger scales? That's where things get interesting. Dark flow. In the early 2000s, astronomers analyzed data from NASA's Wilkinson Microwave Anisotropy probe, which measured the CMB, and found something unexpected. They discovered that galaxy clusters across hundreds of millions of light-years seem to be moving in the same direction, with peculiar velocities of around 600 to 1,000 kilometers per second. This movement was not aligned with the gravitational pull of known large-scale structures like the Great Attractor or the Shapley supercluster, but instead appeared to point towards a region far beyond the observable universe. This mysterious phenomenon became known as dark flow. Imagine you in a car driving on a highway and you see another car in your rearview mirror that seems to be moving faster than the speed limit. At first you might think, wow, that driver must be really speeding. But then you realize that maybe you're the one who's slowing down. That's kind of like what happened with the discovery of dark flow. At first, astronomers thought that maybe there was something wrong with their data or their analysis. But as more and more studies confirmed the original findings, they realized that there might be something new and exciting going on. One possible explanation for dark flow is that the universe is not as uniform or homogeneous as we once thought. In other words, there might be regions of space that are more dense or massive than others, which could create a sort of gravitational drag on galaxy clusters, pulling them in a particular direction. Another possibility is that dark flow is evidence of something even more exotic, such as the influence of extra dimensions or other hypothetical objects or phenomena that we have not yet detected. The mystery deepens. Since its discovery, dark flow has remained an enigma, defying a simple explanation. Some scientists have suggested that it might be a sign of new physics beyond the standard model of cosmology, which describes the evolution of the universe in terms of matter, energy, space, and time. Others have proposed that dark flow could be evidence of a modification to Einstein's theory of general relativity, which has been remarkably successful in explaining the behavior of the universe on large scales. One way to think about this is that general relativity is like a set of rules for how the universe works. And so far, those rules have been confirmed by countless observations. But dark flow seems to be a phenomenon that cannot be explained by those rules. It's like discovering a new law of nature that doesn't fit into our existing framework of knowledge. Of course, any new theory that explains dark flow would have to be consistent with all the observations that currently fit within the standard model, so it would be a real challenge to come up with a solution. Nevertheless, the possibility of uncovering new physics is what makes dark flow so exciting for many scientists. The implications. If dark flow turns out to be real, it could revolutionize our understanding of the universe. For example, it could provide evidence for the existence of extra dimensions or alternative theories of gravity. It could also tell us more about the distribution of matter in the universe and help us understand how galaxies form and evolve. Imagine we're standing on a beach watching the waves crash onto the shore. If we only look at a small section of the beach, it might seem like the waves are just randomly crashing up and down. But if we step back and look at the bigger picture, we can see that the waves are actually part of a larger pattern. Dark flow might be like looking at a bigger pattern in the behavior of the universe that we have not seen before. It could help us understand the fundamental laws of nature and our place in the cosmos. And who knows? Maybe one day we'll even discover what's causing the strange motion of the galaxy clusters. What do you think? Do you think dark flow is evidence of new physics or something else entirely? What did Alexander Koshelinsky see in 2008? Did he discover an enormous structure outside of our observable universe, a so-called tiling of the cosmos? Did he find evidence that our observable universe is embedded in a greater whole? Or was his detection nothing but a statistical fluctuation, an artifact of his data analysis? And what are the tests that could settle the case? If the foundations of cosmology describe the universe as smooth and isotropic on the grandest scales, then the discovery of dark flow depends on objects and phenomena that break that symmetry in subtle but measurable ways. To grasp why this idea is so provocative, we need to explore the tools and objects that serve as both cosmic test cases and benchmarks. Dipole anisotropies, galaxy clusters, and the large-scale flows of matter. The CMB dipole. Our own motion written on the sky, the cosmic microwave background is often described as the most uniform signal in nature. The same in all directions to 1 part in 100,000. But one exception stands out. The dipole anisotropy. When we map the CMB across the entire sky, one hemisphere looks slightly warmer and the opposite slightly cooler. This isn't because the early universe itself was hotter in one direction. Rather, it's because we are moving relative to the CMB rest frame. The solar system, as measured by WMAP and Planck, moves at about 370 kilometers per second toward the constellation Leo. This dipole anisotropy is an anchor point. It confirms our own peculiar velocity through the cosmos. So the CMB dipole is the first iconic object in the story of dark flow, the baseline against which all other large-scale motions are measured. Galaxy clusters as beacons. If the dipole reveals our motion, galaxy clusters reveal the motion of the universe's largest bound structures. Galaxy clusters are enormous, tens of millions of light-years across, containing thousands of galaxies, huge amounts of dark matter, and vast reservoirs of hot plasma. Because of their sheer mass, they are the best tracers of large-scale cosmic flows. Clusters also interact with the CMB in a special way, through the Sunyaev-Zeldovich SZ effect. The thermal SZ effect distorts CMB photons as they pass through hot intracluster gas, while the kinematic SZ effect KSZ imprints the velocity of the entire cluster relative to the CMB. By stacking data from hundreds of clusters observed in X-rays and comparing them to WMAP's CMB maps. Researchers led by Alexander Koshlinsky in 2008 announced the detection of a bulk motion of galaxy clusters, all drifting in a common direction, toward the constellations Centaurus and Hydra. This was the first dark flow claim. The velocity was estimated to be up to 1,000 kilometers per second, extending to distances of at least 800 million light-years. The Great Attractor and Shapley supercluster skeptics of dark flow often point to known massive structures within the observable universe, such as the Great Attractor and the Shapley supercluster. The Great Attractor is a dense region of galaxies and clusters about 150 to 200 million light-years away. It exerts a measurable pull on the Milky Way and other galaxies in our local region. The Shapley supercluster, even larger, lies about 650 million light-years away and is one of the most massive concentrations of galaxies in the nearby universe. Could the observed bulk motion of clusters simply be the result of these attractors? The problem is scale. While these structures explain some peculiar velocities locally, the dark flow measurements extend to much greater distances and seem to remain coherent well beyond where the influence of known structures should fade. If real, that suggests the cause is not inside the observable universe. Dipoles beyond the CMB X-ray and radio sky anomalies. The CMB dipole is not the only dipole anisotropy in astronomy. Surveys of galaxies in X-ray and radio light have revealed unexpected alignments. Large-scale distributions that seem to echo the same preferred direction as the dark flow measurements, for example. X-ray cluster surveys by NASA. Shah-1 and Razat missions showed anisotropies in the distribution of hot gas. Large-scale radio galaxy counts also reveal an apparent excess in one direction. These alignments are controversial, but if confirmed, they suggest that multiple cosmic signals, from radio galaxies to galaxy clusters to the CMB itself, be pointing toward a shared axis of large-scale motion. Y clusters or the key clusters are crucial because they serve as both tracers of structure and direct probes of motion. Unlike individual galaxies, which can be scattered by local effects, clusters represent the largest gravitationally bound entities. If they are all streaming in the same direction, it implies something coherent and large-scale at work. This is why Koshlinsky's dark flow announcement was so provocative. It wasn't about one galaxy or even one supercluster. It was about hundreds of clusters across billions of light-years, apparently marching to the same cosmic beat. The tension with cosmology, the standard cosmological model, CDM, which includes dark energy, cold dark matter, and an inflationary Big Bang, predicts that on scales larger than about 100 million light-years, peculiar velocities should diminish. The universe should look smooth and random in all directions. But if galaxy clusters across gigaparsecs are truly flowing in one direction, this breaks that assumption. It could mean that there is a previously unknown superstructure beyond the horizon. Our universe is being influenced by conditions outside of it. Or the signal is a statistical artifact, a product of how the data was processed. Each of these possibilities is dramatic in its own way. A new study now, a new study has appeared, also based on galaxy clusters and the Sun-Yave-Zeldov effect. It was conducted by a team of astrophysicists led by Lemaire de Rose from the Institute for Advanced Study in Princeton. They used data from the Planck satellite to measure the large-scale motion of galaxy clusters and cross-correlated their results with the distribution of the cosmic microwave background. They found no evidence of dark flow. In fact, the results are in excellent agreement with the predictions of the concordance model of cosmology. In their paper, the authors discuss the differences between their results and those of the earlier studies. In particular, they point out that the previous studies were based on flux-limited samples of galaxy clusters. This means that the sample contains more distant clusters than closer ones, because of the faintness of the signal. One might expect that the farther away a cluster is, the less reliable its redshift will be. Indeed, the new study demonstrates that the redshift errors of the flux-limited samples are large enough to wash out any signal of bulk flow. But the devil is in the details, and there are more things to consider. What is the exact functional form of the flow? How does it depend on the scale? How does it depend on the position in the sky? We don't know the answer to these questions before carrying out the analysis. Instead of assuming a functional form, the de Rose team used a technique called principal component analysis to identify large-scale flows without any a priori assumptions. It would be premature to declare the issue of dark flow settled. The study by de Rose et al. Has some limitations that prevent it from being definitive. In particular, it does not take into account the peculiar velocity of the Earth relative to the cosmic microwave background. One reason for this is that this velocity is very well determined and agrees with the expected value based on the motion of the Milky Way in the local group of galaxies. Another reason is that including the dipole breaks the rotational invariance of the flow, which makes the flow field ambiguous up to rotations. Since the principal component analysis is rotationally invariant, it is better suited for the study of bulk flows without prior assumptions. However, one could argue that it is justified to use a different method, when one has a good theoretical prediction for the velocity field. Indeed, including the dipole in the analysis would make the dataset more constraining. Another limitation of the new study is that the signal-to-noise ratio of the data is quite low. This is because the Sun-Yave-Zeldovich effect is very weak and difficult to detect. In practice, one has to rely on the statistical anisotropy of the fluctuations of the CMB. The low signal-to-noise ratio is one of the reasons why the authors are reluctant to draw firm conclusions. A more precise measurement of the CMB temperature fluctuations would considerably reduce the uncertainty of the flow measurement. What would a flow signal tell us? Interestingly enough, even if one takes the rather conservative view that the signal of dark flow is too weak to be detected with current instruments, this too can be used to constrain cosmological models. The upper limit on the amplitude of the flow as derived by the de Rose group excludes a significant class of models for modified gravity. Such a test of modified gravity was proposed already in 2011 by Stacy McGaugh and I in a paper in Physical Review D. If we find evidence for dark flow, what would it tell us? The simplest explanation would be that we live in a universe with large-scale structure beyond the horizon. It would be a universe with fractal structure on scales much larger than the size of the observable universe. This would require a modification of the current cosmological model. The question would then be, how exactly do we have to modify our ideas about the structure of the universe? The flow could also indicate that our universe is embedded in a greater whole, maybe in a multiverse, and that it is subject to external influences. What kind of multiverse are we talking about here? Is it the eternally inflating chaotic multiverse of eternal inflation, or the static ensemble of the multiverse of the eternal inflation models? Does the flow come from another universe in the ensemble, or from the eternally inflating regions outside our observable patch of the universe? The third possibility is that the dark flow is nothing but an artifact of data analysis. I personally find this scenario increasingly unlikely. However, we have to keep in mind that it is possible that we missed some relevant systematics. I find it amazing how much information is encoded in the tiny temperature fluctuations of the cosmic microwave background. Not only did it reveal the birth of the universe, it may also unveil its ultimate fate and possibly provide evidence for physics beyond our current understanding. The enigma of cosmic motion. In the grand theater of the cosmos, galaxies pirouette in an intricate ballet. Their movements, however, are not random. They're drawn together and pushed apart in ways that hint at an underlying order. But what's choreographing this cosmic dance? Is it a grand design or the echoes of an ancient beginning? And what does it reveal about the fate of our universe? As we peel back the layers of this cosmic choreography, we find ourselves confronting not just the nature of the present, but also the fate of the universe. Our quest to understand the movement of galaxies began with simple assumptions. We imagined a universe in perfect balance, unchanging over time. But soon, anomalies appeared. Tiny perturbations that didn't fit the picture of a static cosmos. In the 1920s, Edwin Hubble made a groundbreaking discovery. He found that distant galaxies were all racing away from us, not randomly, but in a uniform expansion of the universe. This observation not only shattered the notion of a static universe, but also laid the foundation for the Big Bang theory. It was as if someone had rewound a film of the cosmos, placing all the galaxies close together in an instant. Then, with the click of a button, the film began to play forward, showing these galaxies flying apart. The stage was set for the grand cosmic ballet, and the music swelled with the birth of the universe and the Big Bang. But as our instruments became more refined, the choreography grew more complex. In the late 1970s, a peculiar pattern emerged. Galaxy clusters seemed to be drawn together into filaments and sheets, forming a vast network across the universe. This revelation gave rise to a new concept, dark matter, postulating a type of matter invisible to the naked eye. Yet holding galaxies together, scientists wove a new narrative into the cosmic ballet. Dark matter became the unseen choreographer, its gravitational pull binding galaxies into intricate patterns. Yet even as we marveled at this grand spectacle, some scientists noticed a disturbing dissonance. A few galaxy clusters, like the Shapley supercluster, seemed to be moving too fast, as if something outside the grand choreography was pulling them along. Others saw hints of a directional bias, a subtle preference for movement in certain directions which shouldn't exist in a perfectly balanced universe. Damn. These observations hinted at an unsettling possibility that the music driving the cosmic ballet might not be the harmonious hum of dark energy, but a discordant tune from beyond the observable universe. In 2008, a study published in the journal Physical Review D sent ripples through the scientific community. It proposed that our universe is merely a bubble in a vast cosmic foam, a multiverse. According to this theory, our universe expands faster than the speed of light, creating an impenetrable wall that prevents us from peering into the neighboring bubbles. Each bubble, with its own laws of physics and constants, expands independently, floating like a soap bubble in a frothy sea. And just as bubbles in a soap solution can collide, so can universes in this cosmic multiverse. This collision, however, would not be a gentle merging, but a violent clash of expanding realms. Yet despite these chaotic collisions, each bubble remains isolated, forever expanding, forever shrouded in darkness. The implications of such a discovery would be nothing short of revolutionary. It would suggest that our universe is but one of many, each with its unique story to tell. Our existence, therefore, would be a rare occurrence, a unique note in the grand symphony of the cosmos. The question is, can we hear that symphony? Can we detect the whispers of other universes as they brush against our own? What would it mean for our understanding of reality if we did? Enter dark flow. In 2014, a group of cosmologists led by the British physicist Richard Planck proposed that the peculiar motions of galaxy clusters could be explained by the gravitational pull of neighboring universes. These neighboring universes, existing just beyond our observable horizon, exert an invisible influence on our own, a phenomenon dubbed dark flow. The idea was both tantalizing and unsettling. It suggested that the very structure of the universe is more complex than we imagine, that there is more out there than meets the eye. But why do we care about this dark flow thing? Why should you care? Let me tell you. You see, our universe, as vast as it is not entirely comprehensible to us. We can only observe a portion of it, a sphere around Earth with a radius of about 13.8 billion light-years. This limitation stems from the finite speed of light. No matter how fast we send signals, they cannot travel faster than light. so there is a limit to how far we can see in space and time. Consequently, our universe is often referred to as the observable universe. What lies beyond this observable limit is shrouded in darkness, hidden from our perception. However, the fact that we cannot directly observe what lies beyond the observable universe doesn't imply that it doesn't exist. It simply means that we have no direct evidence for or against anything out there. We know that the universe extends beyond what we can see because we can observe galaxies that are moving away from us faster than light. This phenomenon, known as the recession of galaxies, provides strong evidence that the universe is expanding. And if the universe is expanding, it means that there must be more to it than what we can currently observe. The recession of galaxies also tells us that the universe is getting bigger. And not just getting bigger, but getting bigger at an accelerating rate. This acceleration is attributed to a mysterious force called dark energy, which makes up about 68% of the total mass energy content of the universe. Here's where things get interesting. If the universe is expanding and it's doing so at an accelerating rate, then there must be some sort of mechanism driving this expansion. This mechanism could be dark energy, as most cosmologists believe, or it could be something else entirely. In fact, some physicists speculate that there might be other universes beyond our observable horizon. Universes that could be interacting with ours in ways that we don't yet understand. These speculations arise from various theoretical frameworks, including string theory and loop quantum gravity, which propose the existence of multiple universes. In some of these multiverse theories, the other universes are thought to be separated by vast stretches of spacetime known as wormholes. Through these wormholes, particles or even light could pass from one universe to another, potentially carrying information with it. This raises a fascinating question. Could the accelerated expansion of our universe be due to the combined effects of dark energy and the exchange of matter and energy with neighboring universes through wormholes? If this were true, it would suggest that the behavior of our universe is intricately linked to the properties of these neighboring universes. Conversely, changes in our universe could also affect the behavior of other universes. Such an interconnectedness challenges our intuitive understanding of the universe as a collection of independent systems. Instead, it paints a picture of a cosmos where everything is linked together in a grand web of interaction. Let's take a closer look at dark flow itself. While dark flow remains a highly debated topic in cosmology, there is another area of research that offers intriguing insights into the motion of galaxies. In the early 1930s, the German physicist Friedrich Hoyle coined the term steady-state theory to describe a universe that never changes. Unlike the Big Bang theory, which posits that the universe evolved from a hot, dense state, the steady-state theory assumes that the universe has always been and will always be the same. Central to this theory is the concept of the cosmological principle, which asserts that the universe is homogeneous and isotropic. Homogeneity means that the universe looks the same in all directions and at all points, while isotropy means that it behaves the same way in all directions. Now, you might be wondering, why would anyone propose such a theory in the face of mounting evidence for the Big Bang? Well, in the 1940s, Fred Hoyle, together with Sir Hermann Bondi and Thomas Gold, came up with the steady-state model as a viable alternative to the Big Bang. They argued that the observed expansion of the universe could be explained without invoking a beginning or an end. Instead, they proposed that new matter was continuously created to keep the universe perpetually in a state of balance. However, as more observations accumulated, the steady-state theory faced increasing challenges. The discovery of the cosmic microwave background radiation in 1965 dealt a significant blow to this theory. The Big Bang theory accurately predicted the existence and properties of this radiation, whereas the steady-state theory could not. Nevertheless, the steady-state theory had a profound impact on the development of cosmological ideas. It introduced the concept of dark matter, which was initially seen as a way to make the steady-state theory more compatible with observations. In fact, in 1935, J. Robert Oppenheimer and Hartland Snyder used general relativity to show that the Big Bang singularity could be avoided if the universe contained a sufficiently large amount of matter. This matter, known as dark matter, would counteract the gravitational collapse of the universe, preventing it from collapsing in on itself. Today, dark matter is widely accepted as an essential component of the universe, making up about 27% of its total mass-energy content. But while dark matter has become a cornerstone of modern cosmology, the steady-state theory has largely been abandoned. And now we arrive at a pivotal moment in our cosmic journey. With our discussion of dark flow, we've ventured into a realm where the foundations of cosmology are challenged, where the very fabric of our universe is subject to speculation. It's important to remember that while dark flow offers an intriguing perspective, it's just that, a perspective, a lens through which we can view the universe. It does not necessarily represent the absolute truth. Rather, it invites us to question our assumptions, to refine our tools, and to push the boundaries of our understanding. Whether dark flow proves to be a valid theory or an artifact of our perception, the process of exploring this concept enriches our understanding of the universe. It compels us to consider the limitations of our knowledge and the fallibility of our instruments. It reminds us that science is not a static body of knowledge, but a dynamic process of discovery and refinement. The future of our understanding of the universe hinges on our ability to embrace these uncertainties, to grapple with the complexities of our observations, and to refine our theories accordingly. The universe, with its infinite wonders, continues to beckon us to explore, to question, and to discover. And as we venture deeper into the cosmos, we carry with us the spirit of inquiry, the thirst for knowledge, and the courage to confront the unknown. So what do you think? Does dark flow intrigue you? Do you find the idea of a multiverse compelling, or do you think it's just a statistical fluke? Dark energy is one of the biggest mysteries in physics, making up around 2/3 of the entire universe. Dark flow. Well, that's a weird phenomenon which could turn our understanding of the cosmos on its head. But what exactly is dark flow? Is it real, and why should you care? In this video, we'll answer those questions and hopefully more along the way. But first, a quick message from this video's sponsor. Every year brings new discoveries in space. NASA missions touch the sun. Rovers explore distant planets, and rovers explore distant planets. Observatories peer deep into the cosmos. But one of my favorite stories every year comes from the James Webb Space Telescope, which continues to amaze and inspire with its incredible views of the universe. Alright, let's get back to the video. The idea of dark flow was proposed in 2007 by a group of physicists led by Princeton University's David Kipping. They wondered if the large-scale bulk flow of matter in the universe could leave an imprint on the cosmic microwave background, or CMB. This faint afterglow of the Big Bang could show signs of this motion, and those signs could help us determine the overall shape of the universe. The trouble is, though, interpreting the CMB is complicated. It's very difficult to sift through all the data and pinpoint any signal amidst the noise. So instead of looking directly at the CMB, Kipnis and his colleagues took a roundabout approach. Instead of analyzing the CMB directly, they looked at how galaxies were moving relative to the CMB. You see, galaxies don't move only because of gravity. They also move because of the large-scale flow of the universe's contents. And because we know how fast the universe is expanding in general, we can estimate the relative motion between galaxies. If there's a dark flow, we expect to see an overall pattern in galaxy motions, a sort of bulk flow superimposed on top of the Hubble flow caused by the universe's expansion. To find out if this is true, the team studied data from the Sloan Digital Sky Survey, which contains three-dimensional positions of hundreds of thousands of galaxies. They measured how fast galaxies were moving in different directions and found that there could be a significant flow of galaxies in one particular direction. This apparent flow could be due to our own Milky Way moving through a hypothetical dark flow. Alternatively, the dark flow could be caused by large-scale inhomogeneities in the matter distribution, or perhaps something else. But here's the thing. The effect wasn't very strong, and it could easily have been caused by errors in the data or other factors. Nonetheless, the paper generated a lot of attention and sparked further research. One of the most comprehensive studies to date was published in 2018 by a team led by Wendy Friedman at the University of Chicago. They used data from the 2-degree microwave sky survey to analyze the CMB's temperature fluctuations. These fluctuations provide a map of how matter was distributed in the early universe, which in turn affects the way galaxies form and evolve. Friedman's team looked for correlations between the patterns in the CMB and the distribution of galaxies. They wanted to see if there is any preferred direction in the distribution of galaxies that might signal dark flow. Their analysis revealed a slight tilt in the galaxy distribution, but they concluded that it could be explained by a peculiar velocity of the Milky Way. Now, before you get too excited, this peculiar velocity is essentially our galaxy's speed and direction relative to the rest of the universe. We know that the Milky Way moves around the galactic center at around 220 kilometers per second, and that it's also moving through space towards the constellation of Great Dog at around 630 kilometers per second. However, these speeds are quite small compared to the typical speeds of galaxies that we're interested in when talking about dark flow. So even if we account for these peculiar velocities, there's still a small discrepancy left over. Still, it's important to note that even if the study's authors came to the conclusion that dark flow might be present in the data, it was too weak to make a definitive statement either way. So if dark flow has been so hard to detect, why do we keep searching for it? Well, for one thing, the idea has attracted a fair amount of attention from scientists who believe that the current cosmological model needs revision. You see, the standard model of cosmology, often called lambda CDM, contains several key components. Lambda represents dark energy, a mysterious force that makes up around 2/3 of the universe and causes the universe to expand at an accelerating rate. CDM stands for cold, dark matter, a hypothetical form of matter that makes up around 1/4 of the universe, and does not interact with baryonic matter, the stuff that makes up stars, planets, and people. The problem is, despite its success in explaining many observations, lambda CDM has several shortcomings. It fails to explain the matter-antimatter asymmetry in the universe, the observed large-scale structure of the cosmos, and it predicts to much small-scale structure. Many scientists therefore hope that dark flow could be evidence of a new type of physics that resolves these problems. It's also worth noting that dark flow could provide an explanation for other anomalies in cosmology, such as the so-called Hubble tension. This tension arises because different measurements of the universe's expansion rate give different results. One way to resolve the tension is to introduce a new type of matter with a negative pressure that changes the expansion rate of the universe over time. Such matter would cause the universe to expand faster now, which could explain why recent measurements of the expansion rate are higher than expected. However, it's important to keep in mind that dark flow isn't the only explanation for the Hubble tension. Other possibilities include modifications to Einstein's theory of general relativity. Nonetheless, the search for dark flow continues. Some scientists believe that it could be detected in future surveys such as the Dark Energy Spectroscopic Instrument, which will measure the positions and velocities of tens of millions of galaxies. Others are looking for signatures of dark flow in the CMB, using data from the Planck satellite and other experiments. And there's one more thing. You see, if dark flow exists, it could be related to another intriguing phenomenon known as the cosmic microwave background anomaly, known as the axis of evil. This axis of evil is an apparent alignment between the Earth's location and the patterns in the cosmic microwave background. It's not a physical axis, just a statistical correlation that has sparked debate among cosmologists. Some scientists argue that the axis of evil is a real feature of the universe that could indicate a preferred direction in space. Others claim that it's a selection effect caused by the way data is analyzed. The jury is still out on this one, but it's possible that dark flow could shed light on the mystery. If the preferred direction inferred from the axis of evil matches the direction of dark flow, it would be hard to dismiss it as a mere fluctuation. So what does this all mean for us? If dark flow is real, it could revolutionize our understanding of the universe. But if it's not, it will simply reinforce the prevailing view that the universe is homogeneous and isotropic. Either way, the search for dark flow is pushing the boundaries of our knowledge about the cosmos and reminding us of how much we still do and understand. I find this stuff endlessly fascinating. But what about you? Let me know in the comments below. And speaking of things that are fascinating but just out of reach, in the vast expanse of our universe, where galaxies spin and stars ignite, there's a secret current that's challenging everything we know. Imagine if I told you that our universe itself is flowing in a way we can't see, that there's a dark current carrying galaxies along with it. And even stranger, it seems to be speeding up. Sounds like science fiction, right? Well, believe it or not, this isn't the plot of a thrilling space movie. It's an intriguing scientific theory that's making waves in the world of cosmology. But hold on, how can we even know such a thing? You're about to embark on a journey through the cosmos as we explore the mind-boggling concept of dark flow, phenomenon so elusive it challenges the very fabric of our understanding of the universe. Join me as we delve into the heart of the Milky Way and uncover the secrets hidden within the enigmatic maps of the cosmic microwave background. You won't want to miss this. To understand how scientists even think this might be possible, we need to take a deep dive into the fascinating world of the cosmic microwave background, or CMB. Think of the CMB as a baby picture of the universe. It's the faint afterglow of light that filled the cosmos when the universe was just a few 100,000 years old. The universe was hot and dense back then, filled with a sea of particles like protons, neutrons, and electrons. As the universe expanded, these particles combined to form atoms, mostly hydrogen. And once the universe cooled enough, light finally started to stream freely. This ancient light, stretched by the expansion of the universe over billions of years, has reached us today as the CMB. One of the most incredible things about the CMB is that it's almost perfectly uniform no matter which direction you look in the sky. It's this uniformity that makes it so special. It's a snapshot of the early universe, a time when the universe was incredibly homogeneous, or the same throughout. But wait, did you catch that? I said almost perfectly uniform. There's a tiny variation in the temperature of about 1 millikelvin, or 1,000th of a Kelvin. That may sound small, but trust me, in the world of cosmology, it's a big deal. These tiny variations in temperature encode a wealth of information about the early universe. They tell us about the distribution of matter in the universe, the abundance of different elements, and even the age of the universe itself. Over the years, scientists have developed sophisticated tools to analyze the CMB and extract its secrets. Enter WMAP and Planck, two groundbreaking space missions that have revolutionized our understanding of the CMB. WMAP, the Wilkinson Microwave Anisotropy Probe, was launched by NASA in 2001. Its mission was to measure the polarization of the CMB, which could provide clues about the universe's evolution in the first moments after the Big Bang. After 9 years of exploring the cosmos, WMAP provided us with an incredibly detailed map of the CMB. It revealed the universe to be 13.8 billion years old, supported the existence of dark energy, and confirmed the flatness of the universe. But WMAP also provided the first evidence of something strange, a possible flow in the distribution of galaxies. This discovery shook the foundations of cosmology and opened up a Pandora's box of questions and debates. After WMAP, it was Planck's turn to take center stage. Launched by the European Space Agency in 2009, Planck was designed to measure the temperature of the CMB with unprecedented precision. With a sensitivity of 1 microkelvin, Planck was able to map the CMB with an accuracy that had never been achieved before. Planck's findings largely confirmed those of WMAP, providing further evidence for the Big Bang theory and the Standard Model of cosmology. However, Planck also had its own surprises in store. It provided an even more precise measurement of the age of the universe, 13.787 billion years, and refined our understanding of dark energy and dark matter. But like WMAP before it, Planck also had its own anomalies, tiny fluctuations in the CMB that didn't quite fit with the predictions of the Standard Model. Now let's talk about the elephant in the room, the discrepancy between WMAP and Planck's findings regarding the possible dark flow. WMAP detected an unusual pattern in the CMB, suggesting that our universe is expanding in a non-uniform way. In other words, it seemed as though the universe itself was flowing in a particular direction. This discovery sent shockwaves through the scientific community. Proponents of the dark flow hypothesis argued that it could provide an alternative explanation for the observed expansion of the universe, potentially challenging the current cosmological models. On the other hand, critics argued that the detection was nothing but a statistical fluke, a random variation in the data that doesn't reflect the true nature of the universe. When Planck came along and couldn't replicate WMAP's results, it seemed to put an end to the dark flow debate. However, the story doesn't end there. Some scientists argue that Planck's analysis was flawed and that it failed to account for the full complexity of the CMB data. They claim that the true signal of dark flow is still present in the data, but it's much fainter than originally thought. buried beneath layers of noise and requiring sophisticated statistical methods to unearth. This means that while Planck may not have found clear evidence of dark flow, it doesn't necessarily disprove its existence. Instead, it merely adds another layer of complexity to an already puzzling cosmic mystery. One of the main points of contention is the method used to analyze the CMB data. Supporters of the dark flow hypothesis argue that traditional methods do not take into account the full complexity of the signal, leading to a distorted view of the universe's behavior. They propose new statistical techniques that consider the nonlinear relationships and evolving nature of the signal, potentially revealing a more accurate picture of the universe's expansion. This debate is a testament to the power of human curiosity and the relentless pursuit of knowledge. Despite the lack of conclusive evidence, scientists continue to explore all possible avenues to understand the true nature of the universe and its expansion. The quest to understand dark flow has also pushed the boundaries of technology, driving innovation in fields such as astrophysics and cosmology. As scientists strive to detect the faintest signals from the depths of space, they develop new instruments and techniques that can peer deeper and observe phenomena that were once thought to be impossible to detect. For example, the Atacama Cosmology Telescope in Chile is one of the latest instruments pushing the limits of our observational capabilities. With its advanced technology, it aims to measure the polarization of the CMB with unparalleled precision, shedding light on some of the universe's deepest mysteries. However, it's important to remember that science is a process of continuous refinement and questioning. No discovery is ever truly final, and every hypothesis must withstand rigorous scrutiny and testing. The scientific community is right to be cautious when it comes to claims about the nature of the universe. Extraordinary claims require extraordinary evidence. While the idea of a flowing universe is fascinating, it's crucial to ensure that any conclusions are well supported by data and free from bias and error. As we continue to explore the depths of space and uncover its secrets, it's natural to feel a sense of wonder and excitement. The idea that there may be something beyond what we currently understand is both intriguing and humbling. It reminds us of the boundless curiosity that drives humanity forward and our insatiable thirst for knowledge. However, it's equally important to approach these discoveries with a healthy dose of skepticism and critical thinking. We must remain open to new ideas, but also cautious not to jump to conclusions. The dark flow controversy is a prime example of this. While it has captured the imagination of scientists and the public alike, it's essential to remember that it remains just a hypothesis until proven otherwise. The universe is vast and complex, and there's so much that we don't understand. What we do know is that our current understanding is incomplete, and that there's always more to discover. The key is to embrace this journey of discovery with an open mind, a critical eye, and a willingness to question everything. Who knows what other wonders and mysteries the universe has in store for us? As we continue to probe the depths of space, we can't help but wonder what else is out there. The discovery of dark flow, whether real or imagined, has pushed the boundaries of our understanding and inspired new ways of thinking about the universe. It's a reminder that the journey of scientific discovery is never truly over, and that there's always more to explore. So as we gaze up at the stars and contemplate the mysteries of the cosmos, let's remember to keep an open mind. Question everything and never stop exploring, because who knows what wonders and mysteries the universe has in store for us. If you found this video insightful, please consider subscribing and supporting our channel. Your support helps us continue to produce high-quality videos that explore the fascinating world of space and astronomy. Is our universe an island in an infinite cosmic sea? Might other universes brush against ours, unseen, unknown? Or are we truly alone in the vastness of existence? Meet the scientific quest to solve one of the most extraordinary mysteries of our time: the dark flow conundrum, a drifting cosmos. Scientists have uncovered a startling possibility. The galaxies in our universe, including our Milky Way, may not be stationary, but are drifting in a common direction at an astounding speed, all seemingly working together in harmony. Imagine a vast cosmic dance where every galaxy is a participant, and our solar system is merely a spectator. Even stranger, this movement seems to be uniform, suggesting a shared purpose, almost as if some invisible hand is guiding them all. But what's even more baffling is the sheer scale of this phenomenon. The galaxies appear to be flowing towards a region in the upper right quadrant of the night sky, If you were to plot their velocities and extrapolate their paths, they converge on a spot known as the Great Attractor, situated around 240 million light-years from Earth. What's even more mind-boggling is the speed at which these galaxies are moving. They're traveling at speeds that range from 722 over 900 kilometers per second. To put that into perspective, that's nearly 4 times faster than the orbital speed of Earth around the Sun. Could there be an invisible force orchestrating this celestial ballet? Or is there something even more extraordinary lurking beyond our understanding? But here's the perplexing part. The galaxies aren't just drifting aimlessly. Their collective motion seems to align with the coordinates of a spot that lies just beyond the observable universe, the limit of what we can currently see. This puzzling alignment has sparked a flurry of theories and speculations among scientists. Is it merely a statistical fluke or a genuine clue pointing to something profound? The implications of such a discovery could be nothing short of revolutionary. If confirmed, it would suggest that our observable universe isn't the whole story. There could be structures, forces, or perhaps even other universes beyond what we can currently detect, subtly influencing our own. So where do we go from here? How can science test an idea that by definition lies beyond the observable universe? The future of dark flow research lies in building better eyes on the cosmos. First, we'll need to refine our observations of the flow's source, the distant galaxy clusters. As our instruments improve, they should resolve the apparent bulk flow into individual galaxies. If dark flow exists, these instruments may finally measure it with confidence. One promising avenue is the study of the cosmic microwave background, the afterglow of the Big Bang. Upcoming experiments like Simon's Observatory and the Square Kilometer Array will scrutinize the CMB's faintest whispers. Their high sensitivity may reveal the imprint of moving galaxy clusters imprinted on the baby universe. Then there's the Vera C. Rubin Observatory, scheduled to begin full operations in the 2020s. Rubin will map billions of galaxies across the sky, tracking their positions and motions. With this treasure trove of data, astronomers may uncover large-scale drifts that align with or refute the dark flow hypothesis. Furthermore, 2 upcoming missions, Euclid and the Nancy Grace Roman Space Telescope, hold immense potential for testing dark flow. Designed to probe dark energy and cosmic structure, these observatories will provide incredibly precise measurements of galaxy clustering. If bulk flows exist, they should reveal themselves in these surveys. By comparing the observed galaxy distribution with theoretical predictions, scientists hope to determine whether the flows persist at scales beyond what standard cosmology predicts. In short, humanity is gearing up with the best tools ever made to test this cosmic mystery. And while each instrument brings us closer to the truth, it also opens up new vistas of exploration. Who knows what other secrets the universe might reveal as we peer deeper into its heart? But let's take a moment to acknowledge the complexity of the task ahead. Measuring dark flow is like trying to detect a friend's whisper in a crowded room full of background noise. Even with the best telescopes, separating the signal from the noise is a monumental challenge. Astronomers must contend with the universe's vastness, the limitations of their instruments, and the sheer volume of data they must sift through. Yet they're undeterred. Armed with advanced algorithms and the power of supercomputers, they're developing innovative ways to extract meaningful insights from the raw data. Their goal is clear: to measure the dipole moment with as much precision as possible, thereby shedding light on the nature of dark flow. Yet even if future data confirm dark flow, it will only be the beginning of a new set of challenges. Confirming dark flow raises more questions than it answers. For starters, if the universe has a preferred direction, why does it seem the same in every direction? Why doesn't it feel like we're drifting through space? Or if other universes exist, why don't we see signs of their presence? In the face of such profound questions, scientists are readying themselves for a deep dive into uncharted territories. If dark flow exists, it will shake the foundations of cosmology. But if they don't, that's still progress. Some alternative explanations already exist. Could be a statistical illusion. The signal Koshensky's team detected could simply be a fluke in the data resolved as instruments improve. Alternatively, local structures within the observable universe could be causing the effect. Perhaps massive voids or filaments of galaxies are tugging on our galactic neighborhood in ways we don't fully understand. But if neither of these explanations holds up, we may need to consider new physics. Could there be modifications of gravity, exotic forms of matter or phenomena we haven't yet imagined? Each possibility leads to deeper insights about how the universe works. What's more, the implications of dark flow extend far beyond the realm of science. It touches upon fundamental questions about our place in the cosmos. Are we truly alone in the grand expanse of existence? Or are there other universes teeming with life? The very notion that our universe might not be the only one is a concept that has captivated philosophers and scientists alike for centuries. The idea of a multiverse, a vast array of parallel universes, has transitioned from a fringe theory to a topic of serious scientific inquiry. Dark flow might be our universe's way of whispering about these extraordinary possibilities. However, before we succumb to these tantalizing prospects, we must tread carefully. Not all scientific minds agree on the interpretation of the dipole moment measurements. Some argue that the apparent flow could be attributed to peculiar velocities, the unique movements of galaxies within clusters or superclusters. They propose that these locomotions, rather than a universal drift, are responsible for the observed signal. Others suggest that the data may contain biases introduced by the limited field of view of the telescopes used in the study. They argue that the dipole moment could be an artifact of the incomplete sampling of the sky, rather than a genuine cosmological phenomenon. Furthermore, critics point out the absence of a comprehensive model that explains the origin and evolution of the alleged dark flow. Without a theoretical framework that elucidates how such a phenomenon could arise naturally, it's challenging to assess its validity. Proponents of the multiverse hypothesis, however, are eager to embrace the implications of dark flow as a potential signal of neighboring universes. They argue that if the dipole moment reflects a true bulk flow, it could indicate the influence of structures or entities outside our observable universe. This intriguing possibility aligns with the predictions of certain multiverse models, where the behavior of our universe is influenced by events or entities in adjacent universes. For those who believe in the multiverse, dark flow becomes a tantalizing clue, a piece of the puzzle, that could connect our universe to the broader cosmic tapestry. However, it's important to approach this topic with a healthy dose of skepticism. Extraordinary claims require extraordinary evidence, and the idea of a multiverse, while captivating, remains highly speculative. Many scientists urge caution, emphasizing the need for further observations and theoretical work before drawing any firm conclusions. Nevertheless, the multiverse question beckons us to contemplate the grand possibilities that lie beyond the observable universe. Could there be other universes, other realities existing alongside or even intertwined with our own? While we may not have all the answers, the very pursuit of this knowledge drives us to explore the depths of the cosmos and the boundaries of human understanding. In conclusion, the dark flow conundrum poses both challenges and opportunities for our understanding of the cosmos. Confirming dark flow would revolutionize our view of the universe. Failing to find it could lead us to reevaluate our assumptions and refine our models. Ultimately, this cosmic mystery compels us to look beyond what we currently know, urging us to seek new perspectives, innovative solutions, and deeper insights into the workings of the universe. The road ahead may be fraught with complexities, but the journey itself pushes the boundaries of human knowledge, and that in itself is a triumph. So what do you think? The idea of a drifting cosmos both intrigue and mystify you? Feel free to share your thoughts in the comments section below. Your insights and opinions matter, and we value your engagement. Also, if you found this video informative and thought-provoking, don't forget to hit the like button and share it with your friends and family. Thank you for joining us on this journey of cosmic discovery. Keep looking up.